As both aldehydes and ketones contain the carbonyl group, they resemble each other closely in most of their properties. The carbonyl group governs the chemistry of aldehydes and ketones in two ways: by providing a site for nucleophilic addition and by increasing the acidity of the hydrogen atoms attached to the alpha carbon. Both of these effects are due to the ability of oxygen to accommodate the negative charge. The typical reactions of aldehydes and ketones are nucleophilic addition reactions. Before we examine the different types of nucleophilic addition reactions, let us first understand the general mechanism of nucleophilic addition reactions. The first step is a slow or the rate-determining step, which involves the attack of a nucleophile on the electron-deficient carbonyl carbon. Since the carbonyl group is flat, it is liable to be attacked from above or below the planar carbon atom. As the nucleophile forms a bond with the sp2 planar carbonyl carbon atom, the electron pair of the carbon to oxygen pi bond shifts to the carbonyl oxygen. The carbonyl oxygen easily accommodates the electron pair to produce a tetrahedral sp3 alkoxide ion intermediate. In the second step, the alkoxide ion captures a proton from the reaction medium to give an electrically neutral tetrahedral product. If the nucleophile is strong, it will readily attack the carbonyl carbon. The resulting addition product can be readily protonated by the solvent or by the added acid. However, if the nucleophile is weak, then it requires an acid catalyst to make the nucleophilic addition reaction occur at a reasonable rate. The acid protonates the carbonyl oxygen to produce an oxonium ion. The oxonium ion is highly reactive towards nucleophilic attack at the carbonyl carbon atom. This is because the carbonyl carbon atom carries more positive charge than it does in the unprotonated compound. The addition of alcohol to the carbonyl group is an example of acid-catalyzed nucleophilic addition. The reactivity of the carbonyl group towards nucleophilic addition depends mainly upon the magnitude of the positive charge on the carbonyl carbon. That is, the electronic factor and the extent of crowding around the carbonyl carbon atom in the transition state. That is, the steric factor. Based on these factors, the order of reactivity is formaldehyde without any alkyl group is more reactive than other aldehydes with one alkyl group, which, in turn, are more reactive than ketones that contain two alkyl groups. Electronically, alkyl groups are electron-releasing groups that release electrons and stabilize the carbonyl carbon by reducing the magnitude of positive charge on it. Hence, the electrophilicity on the carbonyl carbon, and therefore the reactivity, decreases with an increase in the number of alkyl groups. Sterically, the presence of bulkier alkyl groups in ketones hinders the approach of the nucleophile towards the carbonyl carbon. Hence, the bulkier the alkyl group, the lesser is the reactivity. Therefore, the decreasing order of the reactivity of ketones is acetone is more reactive than ethyl-methyl ketone, which is more reactive than isopropyl methyl ketone, methyl tertiary butyl ketone. An aryl group has an electron withdrawing inductive effect, So, it is expected to destabilize the reactant and speed up the reaction. However, it seems to stabilize the reactant even more by resonance, and thus decreases the reactivity. Thus, propanal is more reactive than benzaldehyde because the polarity of the carbonyl group is reduced in benzaldehyde as shown. Now let us look at some important examples of nucleophilic addition on the carbonyl group. These include addition of hydrogen cyanide, addition of sodium bisulfite, addition of Grignard reagent, addition of alcohols, addition of ammonia and its derivatives. When hydrogen cyanide is added to the carbonyl group of aldehydes and ketones, it yields compounds known as cyanohydrins. As HCN is a very weak acid, it is a poor source of cyanide ions. Hence, addition takes place very slowly. Therefore, the addition of a base can generate cyanide ions from the weak acid, HCN, causing a dramatic increase in the rate of the reaction. The cyanide ions, being stronger nucleophiles, rapidly attack the carbonyl carbon to produce the corresponding cyanohydrins. Cyanohydrins are useful intermediates in organic synthesis. They undergo hydrolysis to yield alpha-hydroxy acids or unsaturated acids. For example, the addition of HCN to acetaldehyde yields acetaldehyde cyanohydrin, which, on hydrolysis, yields lactic acid or alpha-hydroxypropanoic acid. Let's look at the addition of sodium bisulfite. When sodium bisulfite is added to an aldehyde or a ketone in the presence of ethanol, it gives a water-soluble solid adduct. This solid adduct is filtered from ethanolic solution and then decomposed by an acid or a base to regenerate the carbonyl compound. Hence, this reaction is used for the purification and separation of carbonyl compounds. For example, acetaldehyde reacts with a saturated solution of sodium bisulfite to give a white crystalline precipitate of acetaldehyde sodium bisulfite. Yet another addition reaction is the addition of a Grignard reagent to the carbonyl group. In this addition reaction, when a Grignard reagent, RMGX, is added to the carbonyl group, with its organic group R being attached to the carbonyl carbon and magnesium to the carbonyl oxygen, it produces an addition compound, which on hydrolysis yields an alcohol. As you can see, formaldehyde produces a primary alcohol, a secondary alcohol with the other aldehydes, and tertiary alcohols with ketones. This relationship arises directly from our definitions of aldehydes and ketones, and our definitions of primary, secondary, and tertiary alcohols. Aldehyde reacts with alcohol in the presence of anhydrous hydrogen chloride to form an unstable intermediate known as hemiacetal. Hemiacetal further reacts with one more molecule of alcohol to give a gem dialkoxy compound known as acetal. This reaction is an example of acid-catalyzed nucleophilic addition in which dry HCl gas protonates the oxygen of the carbonyl group so that the oxonium cation formed is more susceptible to nucleophilic attacks. All steps involved in the formation of acetals from an aldehyde are reversible. Ketones react with an excess of ethylene glycol under similar conditions to form cyclic products known as ethylene glycol ketals. Both acetals and ketals can be rapidly hydrolyzed with aqueous mineral acids, even at room temperature, into aldehydes and ketones respectively. Let's now look at the addition of ammonia and its derivatives. When nucleophiles, such as ammonia and its derivatives, NH2G, are added to the carbonyl group in the presence of acid, they form compounds with carbon to nitrogen double bonds, known as imines. Let's understand the mechanism of this reaction. 1. Initially, the hydrogen ion from the acid attaches itself to the carbonyl oxygen to produce an oxonium cation. 2. This is followed by a nucleophilic attack by the basic nitrogen on the carbonyl carbon to form an intermediate addition product. 3. Further, the elimination of the water molecule from the intermediate results in the formation of the product with the carbon to nitrogen double bond. Since these reactions involve the addition of a nucleophile in the presence of an acid followed by the elimination of the water molecule, they are termed as nucleophilic addition-elimination reactions. Aldehydes and ketones react with ammonia derivatives with the general formula NH2G. Here, G is equal to R, alkyl group, OH, NH2, NH, C6H5, NH, CO, NH2, etc. Aldehydes and ketones react with primary amines to form substituted imines, a Schiff's base. Aldehydes and ketones react with hydroxylamine to form the corresponding oximes. For example, acetaldehyde and acetone react with hydroxylamine to form acetaldoxime and acetoxime respectively. Aldehydes and ketones react with hydrazine, NH2NH2, and its derivatives such as phenylhydrazine, 2,4-dinitrophenylhydrazine, and semicarbazine to form the corresponding hydrazones. For example, acetaldehyde and acetone react with hydrazine to form acetaldehyde hydrazone and acetone hydrazone respectively. Similarly, they react with hydrazine derivatives and form the corresponding hydrazones as shown in the equations here. Hydrazones are usually insoluble solids with sharp melting points. Moreover, oximes and hydrazones, when refluxed with dilute hydrochloric acid, regenerate the parent aldehyde and ketone. Hence, oximes and hydrazone are used for the detection and purification of organic compounds that contain the carboxylic functional group, COOH, are called carboxylic acids. The name carboxyl is derived from the carbonyl group C double bond O and the hydroxyl group OH of which it is composed. Carboxylic acids are widespread in nature. Higher members of aliphatic carboxylic acids, known as fatty acids, are important components of the biomolecules, such as lipids, fats and oils. Aliphatic carboxylic acids have been known for a long time. A large number of them are known by their common names that refer to their sources rather than to their chemical structures. The common names for carboxylic acids are usually derived from Latin or Greek words that indicate the original source of the individual acid. All common names of these acids end with IC acid. For example, the name formic acid, HCOOH, is derived from the Latin word formica, which means red ants, while acetic acid, CH3COOH, is derived from the Latin word acetum, which means vinegar. Similarly, butyric acid is derived from the Latin word butyrum, which means butter. The name caproic acid, which is obtained from goat fat, is derived from the Latin word caper, which means goat. A dicarboxylic acid contains two carboxyl groups. The table here gives the common names of some dicarboxylic acids. Their names can be easily remembered by the mnemonic, "Oh my such good apple." When it comes to substituted acids, the position of the substituent is indicated by the Greek letters alpha, beta, gamma, etc. The carbon adjacent to the carboxylic is assigned the letter alpha, the next carbon beta, the next one gamma, and so on. For example, two methyl groups substituted on the alpha and beta carbons in a 6-carbon carboxylic acid is named alpha-beta dimethyl caproic acid. Aromatic acids are named as the derivatives of benzoic acid, C6H5COOH. For example, compounds A and B shown here are named para-bromobenzoic acid and ortho-para-dinitrobenzoic acid respectively. Methyl benzoic acids are given the special names of toluic acids. For example, the compound shown here is named metatoluic acid. Now, let's look at the IUPAC system. In the IUPAC system, carboxylic acids are named by replacing the ending E of the corresponding alkane by OIC acid to form alkanoic acid. For example, the IUPAC name for carboxylic acid containing one carbon is methanoic acid, obtained by replacing the ending E of methane by OIC acid. Similarly, carboxylic acids containing 2, 3, and 4 carbon atoms are named ethanoic acid, propanoic acid, and butanoic acid respectively by replacing the ending E of the alkanes concerned by OIC acid. For naming the higher numbers, the longest chain containing the carboxyl group is selected, and numbering is done from the side of the carboxyl group, always giving it the number 1. For example, the compound shown here is named 4-methyl-hexanoic acid. For naming compounds containing more than one carboxyl group, the ending E of the alkane is retained, and the multiplicative prefix di, tri, etc. is added to the term oic acid. The position of the COOH groups are indicated by Arabic numeral before the multiplicative prefix. For example, the compound shown here, which contains 3 carboxyl groups on the first, second and third carbons, is named propane. 1, 2, 3 tricarboxylic acid. In the IUPAC system, benzoic acid is named benzene carboxylic acid. Note here that the common name benzoic acid is also accepted as the IUPAC name. If side chains or substituents are present, then they are indicated by numbers, with the carboxyl carbon atom being numbered 1. For example, phenyl acetic acid shown here is named 2-phenyl ethanoic acid. Similarly, phthalic acid is named benzene 1,2-dicarboxylic acid. The name of a salt of carboxylic acid consists of the name of the cation followed by the name of the acid, with the ending IC acid being changed to 8. For example, the compounds given here are named ammonium formate and potassium 2,3-dibromopropionate, respectively.